Hello everyone, this is Dr. Doug Young, and in today's lesson we are going to talk about using the periodic table to determine the atomic structure and to be able to actually draw an atom using what's called the Bohr model, which is going to be perfect for us for these introductory level classes. And then we'll also say a few things about valence electrons, what they mean and how to use the periodic table to figure out how many valence electrons an atom will have fairly quickly. So in previous videos, right, we determined using the periodic table how many protons, neutrons, and electron a given element will have. And so we're going to use that information to draw out the actual atom. So let's pick an example here. Let's just go with, fluorine. So here's fluorine, element number 9. So we're going to use fluorine as our example. And now you may remember from previous videos, right, that we know how many protons fluorine has. It's the same number as its atomic number, right, which is 9. And then it's easy for us to figure out how many neutrons fluorine has, because the neutrons is just the atomic mass, atomic weight, minus the number of protons that it has. And so we're just going to round. You can't really see it underneath my scribbles, but fluorine weighs about 19, which means that there must be 10 neutrons so that the number of protons and neutrons equals 19. And then since we're talking about neutral elements here, right, that fluorine must have the same number of electrons as it has protons, right? So if it's a neutral element, you have to have the same number of protons, same number of electrons, so that your positive charges and your negative charges balance out and you're neutral. So whatever the number of protons that you have, that's the number of electrons you have in any given neutral element. So with this information now, I can start drawing the actual Bohr model here, right? So if you remember from previous videos or readings, the protons are in the nucleus, right? So they're in the very small center. I'm not going to draw 9 individual pieces. I'll just say that there's 9 protons in this nucleus. And like we just said, that apparently for fluorine, there are 10 neutrons in this nucleus. And so I know that those are the very center, and that I have the electrons orbiting or occupying the space around the nucleus. Now what I need to do is I need to figure out how many orbitals or how many shells there are for this given element. And the way we do that is we just simply need to look at what row number, what period that element is in. So if I look at fluorine, right, so remember your periods are your rows. So this is the first, the second, the third period. And fluorine apparently is in the second period. So since fluorine is in the second period, it's in the second row, I know that it has 2 shells or 2 orbitals. So I'm going to draw 2 shells here, right? So what we just said was that the number of shells equals the period that the element is in, right? So that's what we said down here. Since fluorine is in the second period, that it must have 2 shells, right? So for fluorine, it was in the second period, and therefore we had 2 shells. So I know I'm going to have 2 shells. I'm going to have 2 levels that these electrons are in. And I know that I have 9 electrons. So the next question is, well, where do I put all of those electrons? Do I put all of them in the outside shell? Do I put them all in the inside shell? Do I divide them up as evenly as I can? What are the rules for that? And so it turns out that one easy way to remember how many electrons go in each shell is, again, looking at the periodic table. And I'll write this in red here. What you do is that the number of electrons in each shell corresponds to the number of elements in each of the rows. So what I mean by that, right? So if I had just some sort of generic, atom, and you have your nucleus, the idea is that this first shell here, that corresponds to the first period. And if you look at your first period, you'll notice that there is 2 elements, 2 squares in that first period. That's a reminder that I can only fit 2 electrons in that first shell. So that first shell has a maximum of 2 electrons that you could fit in it. If I go to the second shell, and I want to know what's the maximum number of electrons that I can put in that, I go to the second row, and ask how many tiles, how many elements are in that one. And it looks like there's 1, 2, 3, 4, 5, 6, 7, 8. And so there's a maximum of 8 electrons that you can put in that second shell. I could continue with the third shell. If I look at the third shell of some generic, and this is just any atom, this is true for all atoms. If I look in the third shell, I see 1, 2, 3, 4, 5, 6, 7, 8 again. So I can fit 8 electrons in that one. And if I had to keep going, I don't have that much of the periodic table written down here. You guys can look at one you have at home or online. But if you looked at the fourth shell, you'll see that there's 18 tiles, 18 elements there. And so we could, in theory, fit 18 electrons in that fourth one. So 18 in that fourth one. And this, again, is the max number of electrons. This is the maximum number of electrons that you could put in those shells. So I just can't fit any more than that in any one of the shells. So the maximum, the innermost shell could only hold 2 total. The next shell can only hold 8 total. The next one only 8 total. The other one 18 total. And you just keep going on and on down the periodic table. But so the number of electrons for each shell corresponds to that period that you're in. So if I go back to my fluorine example here, right, we said that it has 9 electrons, and the rule is you always start with the innermost first. So you always start with the innermost shell first. So I'm going to start placing electrons in this innermost shell. I have 9 to distribute. So I'm just going to say, okay, here's 1 and 2 in that innermost shell. And again, that's all I can put in here, right? Because we said that you can only fit 2 in the innermost shell. And that means I have 7 more to add. So I must have to add the 7 to the outermost shell. So 1, 2, 3, 4, 5, 6, 7. And I know I can fit 7 in that shell because I could have fit 8 there. In this case, I don't have 8. You don't have to fill the shells. It just means that I was able to put those 7 electrons in that second shell. So I've got my 1, 2, 3, 4, 5, 6, 7 in the outer one, 2 in the inner one for a total of 9. So again, 2 in the innermost, then 8, then 8, then 18. What this means is that fluorine could have room for 1 more electron. It doesn't have 1 more electron, but it could pick up 1 more electron. And this will become important later when we talk about charges and bonds and stuff. But that's what the Bohr model of fluorine would look like, right? That's what this Bohr model is. The Bohr model is exactly what we just drew here. Bohr was the one who was sort of giving credit for figuring out that there were like different shells or different energy levels, different orbitals for these electrons, and came up with this sort of like planetary looking model where it sort of models the solar system, where you have like a big dense thing in the middle like a sun, and then you have small things orbiting that big dense thing, in this case electrons, which are supposed to be analogous to planets. So the Bohr model, also known as the planetary model. Let's do some more examples here. Let's do, for example, let's do lithium. So let's do lithium. Again, if we look at lithium, we have, according to the periodic table, we have 3 protons, we have 4 neutrons, and it looks like lithium is going to also have 3 protons, or 3 electrons, excuse me, because electrons and protons are the same number in neutral things. So I'll start drawing my model out again. I've got 3 protons in the center. I've got 4 neutrons in the center in that nucleus. As far as the number of shells, right, remember that the number of shells is the period that it's in the row. And since lithium here is in the second period, I know that it's going to have 2 shells. So 1 shell, 2 shells. So I've got my 2 shells for lithium. I only have 3 electrons to distribute, but I follow the same rules that I did before, which was I can only fit 2 in the innermost, then 8, then 8, then 18. So I'm going to put the 2 of the 3 in the innermost, and then my third just in that outermost shell. So I've got 2 in the innermost shell, and then 1 in that outermost shell. And that would be my Bohr model for lithium. Pretty straightforward. Let's do a bigger element. Let's do silicon. Same exercise here. Your average silicon has, it looks like about it does have 14 protons. Your average silicon has around 14 neutrons. We're just going to average these out again. And the number of electrons should equal 14 also. So this is all 14s. So I'm going to have 14 protons. I'm going to put my 14 neutrons. Those are both in the nucleus. And then for silicon, silicon is not in the second period, it's in the third period. So that means I'm going to have 3 shells. So let's write my 3 shells. So I've got the first shell, I've got my second shell, and then I've got my third shell. And again, I need to distribute those electrons. So if you go back, right, we said that start with the innermost shell first, which was our one that can only hold 2. So here's 1 electron, 2 electrons. The next shell could hold a maximum of 8, so I'll put 8 there. So with my 2 and my 8, I'm up to 10 electrons. So I've got 10 electrons drawn. But I can't put any more in that second shell because the max is 8, which means now I have to move to that third shell to put my last 4. So 1, 2, 3, 4 electrons. So my Bohr model of silicon would look something like this, where I have my 14 protons, 14 neutrons in the nucleus, 2 electrons in the innermost shell, 8 in the next shell, and then 4 in the last shell. And let's just do one more example. Oxygen. We'll see this example a lot in our classes. It's a super common element. Oxygen, again, if you're looking at the periodic table, looks like it has 8 protons, 8 neutrons, and 8 electrons. And if you're not sure where I'm coming up with these number of protons, neutrons, electrons, definitely recommend that you look at a previous video I did about the periodic table and determining the number of protons, neutrons, electrons, looking at the atomic number and the atomic symbols and masses. So protons and neutrons are still in the middle. Put them down. Oxygen, again, is in my second period here. So it's in the second period, which means, again, 2 shells. So first shell, second shell. 8 electrons, so again, start in the middle. So I got to do my first 2 of 8 in the innermost shell. And then I have 6 more left. I can fit up to 8 in that second shell, so it'll easily hold the 6. So 1, 2, 3, 4, 5, 6. And you notice I'm just kind of putting the electrons wherever in that shell. It doesn't matter if they're like on the top or left or bottom or anything like that. It just needs to be in that shell somewhere. There's no like special orientation for anything. And that's how we draw the Bohr model for oxygen. So here's 3 more examples of the Bohr models. For my students, I do have examples, I do have worksheets, so you can practice more of the Bohr model diagrams if you want. But for the introductory level stuff, the Bohr model takes us really, really, really far, so it's a good model of an atom to start off with. It does get way more complicated really, really quickly, but we don't need to deal with the quantum mechanics stuff, the subshells of like S, P, D, and F. We're not going to talk about any of that stuff at all, so don't sweat that. Now, since we talked about the Bohr model, we kind of want to refine this a little bit, right? We had a lot of electrons in some of those elements, and as you keep going down the periodic table, you're going to have a lot more. We want to talk about the valence electrons, though, as opposed to the total number of electrons. So while oxygen may have 8 electrons, not all of those 8 electrons are really that important in terms of reactivity and bonds and stuff like that. We want to look at what are called the valence electrons, which are defined as the outermost electrons in an atom, right? So they're the ones in that outermost shell, that outermost orbital, so those very outside ones. And they're the most important ones because they're the ones that are going to determine how an element reacts with another element or with itself. In ionic compounds, it's going to help us figure out what the charge is, and in covalent compounds, it's going to tell us, help us figure out how many bonds something could have. So I redrew here for you the, I think we had lithium. Let me write this up here. Here's our lithium Bohr model again. Here's our silicon Bohr model. And here's our oxygen. And so if you look at, for example, lithium, right, for lithium, it has a total of 3 electrons, but if I want to know the outermost electrons, how many valence electrons, it looks like there's just 1. This is the only one. So if I was to write the number of valence electrons, it looks like for lithium, it's just 1. It only has 1 valence electron. It has 3 total, but 2 of them are on inner shells, and only 1 is in the outer shell. So only 1 valence electron. If I go to silicon and I want to know how many valence electrons does silicon have, it's the same deal. Silicon has 14 electrons, but I don't care about the innermost one. I only care about the outermost ones. Those are the ones, again, that are going to react with other atoms to form bonds and transfer electrons and all that sort of stuff. So for silicon, it looks like I have 1, 2, 3, 4 in that outermost shell. So the number of valence electrons that silicon has is 4. So 14 total, but only 4 of them are considered valence electrons. They're the outermost ones, those more important ones. And lastly, oxygen. If I'm looking at oxygen's number of valence electrons, looks like oxygen has 1, 2, 3, 4, 5, 6. 6 valence electrons, 6 in its outermost shell. If you're kind of looking back at the periodic table, you notice that I still have this up here. What's kind of cool is, well, I mean, 2 things. So 1, you can draw the Bohr model of most of these elements, especially the smaller ones that we're going to deal with the most. You can draw the Bohr model and look at this and figure out how many valence electrons there are. That lithium has 1, silicon has 4, oxygen has 8, for example. No problem. But that kind of takes a lot of time to like draw out all of these. But you can use the periodic table really, really quickly to just figure out how many valence electrons something has. So if you look at oxygen here, right, here's oxygen. Here's oxygen. It's in group number, right? If you remember your group numbers, this is group number 1, 2, 3, 4, 5, 6, 7, and 8. So it's in group number 6, right? Oxygen's in group number 6. And you'll notice that that's how many valence electrons it has. So its group number is 6. That's how many valence electrons it has. If you look at silicon, which is right here, silicon is in group number 4. And that's the number of valence electrons it has. And lastly, this is not going to come as a shock to you, lithium, since it's all the way here in group 1, it also has 1 valence electron, right? Group 1 things tend to have one valence electron. Its group number equals 1. Equals 1. So there's this nice general rule that we can state, which is that, you know, for most of the atoms that we're going to talk about, most of the elements that we're going to talk about, the number of valence electrons equals the group number that they're in. So you can just glance at a periodic table and tell how many valence electrons something has. So I'll write that down here. The group number equals the number of valence electrons. The only element probably that I'm going to show any of you at any point where this breaks down is with helium. Because helium does not have 8 valence electrons. Helium only has 2, right? It's only 2 protons, 2 electrons. Helium's over here with the noble gases, though, because, you know, it's a noble gas. It's not over there because it has 2 valence electrons or anything. It's kind of in a weird spot. But aside from helium, this works for most all the elements that we're going to do. So it's really easy. You just find the group number, boom, you've got the number of valence electrons. So let's do a couple quick examples. So if I want to know, for example, how many valence electrons, right? So number of valence electrons of a variety of elements. So here's an atom of an element. You know, what is it for hydrogen or neon or carbon or phosphorus? The idea again is you just got to find the suckers, right? So that's usually when you're starting off, the hardest thing is finding them on the periodic table. But okay, hydrogen's over here. That's in group 1. 3, 4, 5, 6, 7, 8. It's in group 1, so it must have 1 valence electron. That's all I need to know. I don't have to draw the whole Bohr model to figure that out. Neon is over here. It's in group 8. It must have 8 valence electrons. Boom. Again, didn't need to draw the Bohr model to figure that out. Carbon is over here in group 4. Carbon must have 4 valence electrons. Lastly, phosphorus is here in group 5. Must have 5 valence electrons. So that's all you really need to do to figure out the number of valence electrons. So hopefully in this video you've learned a little bit more about how to draw these Bohr models of an atom, so you get a little more sense of their structure, right? That really dense nucleus. Electrons are sort of orbiting, quote unquote, or they're in shells around a nucleus. And then the valence electrons are really the most important electrons that we're going to be looking at, because they're the ones that are involved in bonds. And it's easy to figure out how many valence electrons in a given atom has, because you can just look at the periodic table, find the group number, that's the number of valence electrons. So we're going to use this information and combine it in the next video to talk about the Lewis dot structures of atoms real quick, because that'll be our building block to start making larger compounds, more interesting molecules. So till next time, thanks.